There are different ways to write a chemical reaction equation, and we call them molecular equations, complete ionic equations, and net ionic equations. If you're just given a chemical reaction equation, you are probably given a molecular equation. This is the most common way to write it. But sometimes it can be really helpful to write what we call a net ionic equation, because that shows us exactly what's happening and it gets rid of all the fluff. And the complete ionic equations show us everything exactly as it is. And it's kind of the bridge of getting from the molecular equation to the net ionic equation. To give you a visual representation of what these different equations mean, right here in the middle I've written the molecular equation. I've represented silver nitrate, which is an aqueous solution, the silver being a blue and the nitrate being red. And then it's aqueous, meaning you've got little ions floating around in water. I've done the same thing with sodium and chloride. Now, if you were to mix these two together, you would form a solid precipitate of silver chloride. This might float around in the solution, or it might settle to the bottom. And you would still be left with an aqueous sodium nitrate. So this is the molecular equation, where everything's written as if it were compounds. Although in reality, it looks something more like this. These beakers represent more of what we call the complete ionic equation. The silver is present as an ion, which is separate from the nitrate. Down here on the bottom is more of the net ionic equation. So what's actually happening here is the silver and the chloride are bonding together. But the sodium and the nitrate started their journey as aqueous ions, and they ended their journey as aqueous ions. And so they didn't change, and so they didn't participate in the reaction. And we call that a spectator ion. So what the net ionic equation does is it takes just what participated in the reaction and omits the spectator ions. So let's walk through a couple examples of how you would write a molecular equation, a net ionic equation, through the intermediate of the complete ionic equation. Let's say we wanted to look at the reaction of potassium iodide with lead 2 nitrate. First, we would have to determine what this reacts to form. Now this is a double replacement reaction because we have two compounds. So first we'll look and see the potassium is positive, the iodide is negative, lead is positive, and nitrate is negative. So the potassium will pair with the nitrate, and the lead will pair with the iodide. So then we have lead pairing with iodide. Let's look at their different charges. So iodide we know is a -1. Lead, because it's a double replacement reaction, whatever its charge is over here will also be its charge over here. Over here we know it's a 2+ charge because nitrate has a -1 charge and there's 2 nitrates. So if the lead has a +2 charge and the iodide has a -1 charge, that means that we need 2 iodides to cancel out the charge of that lead. I'm going to put parentheses in here to remind us to go back and look at what state that would be in. Our other product would be potassium and nitrate. Remember to always write the cation in front of the anion. We can look at their charges. Potassium is positive, nitrate is negative, so it already cancels. Now we need to go look at either solubility rules or a solubility chart to help you decide if these solutions would be aqueous or not. An easy rule to memorize is that all group 1 metals are always soluble. So because this has potassium, this is going to be aqueous. If you look at your solubility rules or your solubility chart, you will find that lead 2 iodide is insoluble, meaning it would be in the solid state in this reaction. So what we've written here is the molecular equation. Okay, so that's the molecular equation, but before we can move on, we need to make sure our molecular equation is balanced. Now we can move on to what we call a complete ionic equation. The complete ionic equation writes everything as it actually exists. So if it exists as an ion, then we write it as an ion. This potassium iodide, because it is aqueous, that means that the potassium ions are not connected to the iodide ions. So we would write 2 potassium, and write their charge because it's an ion, in the aqueous state. We also have 2 iodide ions in the aqueous state. We have 1 lead 2+ ion in the aqueous state, and we have 2 nitrate ions in the aqueous state. Notice that if the number is a coefficient, that carries to both of the ions, or if it's written as a subscript, then it only carries to 1. If you have both a subscript and a coefficient, then you multiply them together to see how many ions you actually have. As we move to the product side, this lead 2 iodide is in the solid state, meaning it's present as a compound. It's not present as ions, so we'll leave it as it is. So this forms lead 2 iodide in the solid state. And then, because this is aqueous, we will break it up again to show the ions that are actually present. Now, the rule of thumb is if it's aqueous and it's a strong electrolyte, then you break it up. If it's not aqueous, like it's a solid, a liquid, or a gas, then you leave it together as a compound. And if it's a weak electrolyte, then you would generally leave it together, although we'll leave the discussion of that more for Chem 2 rather than for Chem 1. All right, then once you have your complete ionic equation, that's everything as it's actually existing in the solution, we can from that summarize to a net ionic equation. The net ionic equation looks at this complete ionic equation and asks the question, what hasn't reacted? So if an ion looks exactly the same on one side of the equation as the other side, then it's a spectator. It's not participating in the reaction. For example, this nitrate right here, we have 2 nitrate ions in the aqueous state on both sides of the equation. So this is a spectator ion because it looks exactly the same on both sides. Can you find another spectator ion? So the potassium is the other spectator ion because it looks exactly the same on both sides. If you thought lead or iodide, yes, they are both present in the same number on both sides. That is good because that means it follows the law of conservation of mass. But the state has changed. It's gone from floating around as ions to being clumped together in a compound. So it's different, and so it's part of our net ionic equation. So then we just write the same thing again, but without the spectator ions. And this is your net ionic equation. And this is useful because it helps us to determine what's actually participating in the reaction and write it in its most reduced form. You will most commonly see things written in either a molecular equation or a net ionic equation. I'm going to give you one example and see if you can predict the products, write the molecular equation and the net ionic equation for it. So if we mix magnesium nitrate with sodium phosphate, what is its molecular equation and what is its net ionic equation? Why don't you pause the video and see if you can figure that out. So for the molecular equation, all I have to do is predict these products and balance the equation. The products of this reaction would be magnesium phosphate and sodium nitrate because I'm essentially just switching places of the cations with each other. Note that the subscripts have changed because that's what's needed to make these compounds neutral. Next, I need to go back and make sure the equation is balanced. Now that we have a balanced molecular equation, I can write the complete ionic equation. Every ionic compound that is aqueous, I am going to write as an ion. If it's a solid, a liquid, or a gas, then I'm going to write it as a compound. Now I have a complete ionic equation. At this point, it's always worthwhile to check and make sure everything is still balanced. So I have 6 nitrates and 6 nitrates. I have 6 sodium, 2 phosphate, 2 phosphate, and 3 magnesium. So that's a good indication that everything is still working out okay. The number one thing that people forget to do besides double check is write the charge and the state of every single one. I know it's arduous, I know it takes a long time, but those charges and those states are extremely important to indicating what this reaction actually looks like. If you wrote the sodium ion without the charge, that means you have sodium metal, which reacts violently with water. But if you wrote it with the charge, so sodium ions, it is something that you consume all the time. They're very different things, and so those charges need to be included. Once you have your complete ionic equation, then you're ready to write your net ionic equation. First, find the spectators in the complete ionic equation. This sodium is a spectator, and the nitrate is also a spectator. So I can write my net ionic equation without those spectator ions. And our net ionic equation is 3 magnesium ions reacting with 2 phosphate ions to make magnesium phosphate.